So we're going to start off by taking a quick look at 1.4. If there's things here that you already know how to do, you don't necessarily have to write it down. I'm going to skip most of the examples and save those for you guys in the homework, but I'll do a couple. But I really want to focus on 1.5 because I think that'll be newer than this. So y equals mx plus b. Okay, that's called slope-intercept. Does anyone remember what the m stands for? Yeah. Okay. Slope. And how about the b? Cassidy? Y-intercept. So basically how steep your line is and where it crosses the y-axis. In general, if something is a straight line, it can be written in the form y equals mx plus b. The only condition there is you don't want m to be 0. Because if the slope is 0, then what happens is 0 times anything is 0, and you end up with y equals b. Well, we've been graphing things like that, like in this problem, y equals 20. But technically, y equals a number is a constant function. That's not a linear function. It's constant because it stays the same all the time. To be a linear function, your slope can't be 0. So if we have 2 points, does anyone remember the formula for slope? Using like x's and y's. I know it's rise over run, but I'm looking for something a little different. Luke?
That would be y2 minus y1 over x2 minus x1.
Yep. So your slope is y2 minus y1 over x2 minus x1. Some people remember that as rise over run. There are 2 special cases of slopes. If you have a horizontal line, that's a slope of 0. If you have a vertical line, that is undefined. Undefined. And not only are they special cases of slopes, the equations are also special too, because neither one of these is y equals mx plus b form. I'll mention it in a minute. Horizontal is y equals and then a number, and vertical is x equals and then a number. So let's say we wanted to find the equation of the horizontal and vertical line that goes through the point 2, 3. So here's your point. What would be the equation of the vertical line that the horizontal line that I just drew that goes through the point 2, 3? Yeah, Christian?
Y equals 3.
Yeah, it's y equals 3. And the equation of the vertical line that goes through that point? Yep, Cassidy? X equals 2. Okay, so those are 2 special cases. Not y equals mx plus b, but still lines. The horizontal you can graph on the calculator. The vertical you can't, because the vertical line is not a function, and the calculator only graphs functions. So one thing that you should be comfortable with doing is taking something like 2x plus 3y equals 6 and rewriting it as y equals negative 2/3 x plus 2. That's the same thing. One of them is y equals mx plus b, the other one is not. So you just rearrange it for y by subtracting the 2x. And then dividing through by 3. What's the advantage of writing it that way compared to 2x plus 3y equals 6? It's not the other one's wrong, but yep, pardon?
It's you can graph it from that.
Yep, it's a lot easier to graph. I know I have a y-intercept at 2, and my slope is down 2, right 3. easy to graph. Not that you can't graph it the other way, but most people find graphing in y equals mx plus b pretty straightforward. Now, besides slope-intercept, you can also use point-slope. A little bit different. And that works well if they give you a point and a slope, and you don't know the intercept. So to write an equation in this way, they'll give you a slope, which will be represented by m, and then they'll give you a coordinate on the line. Coordinate anywhere. And that's your x1 and your y1 value, and you fill them into that form. So I'll do an example of this one. They said to use point-slope form to find the equation of this line. That's my x1, my y1, and my m. So it would be y minus 3 equals 1/2 x minus minus 2. So minus and minus becomes a plus. And that's it. That's how you would write the equation of a line in point-slope form. Now, they could ask you to rearrange that. They might say, find the equation and then get y by itself. If that was the case, you'd have to distribute the 1/2 out and then add 3. Any question on how to rewrite that with y by itself? They didn't ask for that, so we don't have to do it. So that's an example of point-slope. And a lot of times we'll use point-slope to find the equation of a parallel or perpendicular line. Does anyone remember what has to happen for two lines to be parallel? They have to have something, okay?
They have to have the same slope.
Same slope and different y-intercepts, because same slope, same intercept, same line. They're not parallel. But same slope, different y-intercepts. Like this. Those are parallel lines. And they have different y-intercepts. How about perpendicular? They don't have to have, it doesn't have anything to do with y-intercepts. You remember that one? Yeah. Hello?
Opposite slopes? Like positive, negative.
Yep, that's part of it. So they have to have, one of them has to be positive, one of them has to be negative. Unless it's the case of vertical and horizontal, then one is 0, one is undefined. That's a little different. But in general, one of them's positive, one of them's negative. Yep, and
They have to be reciprocals.
they have to be reciprocals. So two lines are perpendicular if their slopes are opposite and reciprocals. There's an example. If I said to you, tell me this line that's perpendicular to one with a slope of 2/3, it would be what? Yep, Tennessee.
I thought you were going to say, what was it?
What would be perpendicular to a line with a slope of 2/3?
Do negative 3/2.
Negative 3/2. Those two lines, if you use those as slopes, they would be perpendicular. So the first thing we have to do, if they ask you to find an equation of a line parallel to something or perpendicular, you have to know the slope. In this equation, did they give me the slope directly? No. But I can find it by doing what? Yep. Okay.
Rearranging it into the slope intercept.
Yeah, rearrange it in slope-intercept form. So that would be what? Y equals, we would minus the 3x and then divide by -2. So minus the 3x and divide by a negative. So that would become positive. And the y-intercept, well, I don't even care what the y-intercept is, but the y-intercept would be negative 1/2. So here's your slope. So if I was going to use point-slope form, that's my m, that's my x1, that's my y1. and fill it in, just like we did right here. Now, the only change, if I wrote perpendicular here, well, you tell me, what would be the one thing that would change? If it said to write an equation of a line perpendicular. Yeah, Christian?
The slope would change to negative 2/3.
Yeah. Slope would be negative 2/3, but the x1 and the y1 would stay the same. Okay, any question on that? All right, so the last thing, and then that really finishes up 1.4, is graphing an inequality. It's just like graphing a line, except the difference is sometimes it's a dotted line and you have to shape. In order to graph this, like if it was 2x plus 3y equals 4, what would we want to do first to make that easier to graph? Yeah? Yeah, let's get y by itself. So to get y by itself, I would have to, let's see, minus the 2x. And I would divide by 3. So my slope would be negative 2/3. And my y-intercept, you tell me, what would my y-intercept be? Yeah. 4 what?
Plus
But we'd also have to divide by 3. 4/3. Yeah. Okay. So what I would do is just put a couple points. So you've got 4/3 is your y-intercept. Now go down 2 and write 3. So down 2, write 3. Down 2, write 3. Good enough. Before we draw the line, one thing we have to decide is whether it should be solid or dotted. If you have a less than, a greater than, or a less than, we're going to use dotted. Less than or equal to, greater than or equal to, solid. So in this case, dotted or solid? Well, Renee? It's going to be dotted. So I'm going to draw my line. Kind of like that. Move it. That's pretty good. And make sure we make it dotted. That's one thing that's different with an inequality. First, decide if it's solid or dotted. And the next thing we have to decide is should we shade above it or should we shade below it? Less than or equal to, you shade below. Greater than or equal to, shade above. So in this case, I have a less than. Is that going to be shading below or above? Below. Right, that's all review of stuff that you did. I know it was probably a while ago, back in Algebra 1. Maybe Algebra 2, you reviewed it a little bit. That's section 1.4. Any questions on that? Okay, so I already put up the first part of the homework. Some of you already did it. Those questions right here from page 42. And I'll make sure that'll be in the video as well. All right, so for the rest of class, we're going to look at section 1.5, which is on transformations of quadratics. Every function we study, we're going to look at how to transform it. That means either shifting it, stretching it, or reflecting it. Quadratics are a nice one to look at because they're not too complicated, but they still have enough with them that we can demonstrate all the transformations we're going to be learning. So in general, quadratic functions are written in the form ax squared plus bx plus c. That's how you generally write it when you're getting ready to factor it or use quadratic formula. Now remember, this symbol means real numbers. So what I'm saying here is a, b, and c are real numbers. Technically, this symbol means element of. So what I'm saying is a, b, and c are elements of the real number system. The only restriction is a can't be 0. What would happen if you plugged in 0 for a? Yeah?
It would just be basically self-intercept.
Yeah, if you plugged in 0 for a, you're going to wipe out the quadratic term, and now essentially you have y equals mx plus b. You've made it linear. So a can't be 0 if you want it to be a quadratic.
What does that symbol mean? The ABC?
A, b, and c are elements of the real number system. So in other words, you can use any number you want for a, b, and c, except a can't be 0, but you can't use complex numbers. You have to use real numbers. So let's graph y equals x squared. I think we've done that before. If you have anything, you can clear it. Type in x squared, and we'll do zoom 6. What's that shape called again when you graph a quadratic? Yep. Yep, that's a parabola. And what I want to look at is what happens when you change x to negative x. I'm not going to get rid of y equals x squared. All I'm going to do is everywhere that I have an x in my formula, I'm going to replace it with what it says to in the parentheses. I'm going to replace it with a negative x. And watch what happens when I hit graph. How did that graph compare to the one I drew to begin with? It's the same. I don't know if you can see it, but there's a faint red line on top of the blue one because they're exactly the same graph. Does anybody know what really just happened when I put that negative there? It did do something to the graph, but because of the way this graph looks, you can't tell. You could do the same thing with the letter O. If you did what I'm thinking of, you wouldn't be able to tell you did it. Yeah? It reflected it over the y-axis. Yes. You can't tell because the y-axis is a line of symmetry for the parabola. If you reflect something over a line of symmetry, you can't even tell you did it. I was going to ask you, but I already showed you. The low point in a vertex, in a parabola, that is called the vertex. It could also be the high point if you flip it. That's also a vertex. Yes?
You made it negative x squared, right? Because I didn't do that. It flipped over the x.
If you don't put the parentheses, then that's different. I'll show you what that does after. You might be able to guess already what that does, but we'll look. So the vertex is the lowest, or it could be the highest point in a parabola. So I want to basically play with A. I want to see what happens if we change A. What does that do to the vertex? Every time you change the A, the B, or the C, it does something to the vertex. So let's graph x squared, 1/3 x squared, and 2x squared. all on the same axis. They just put them in y1, y2, and y3. So I want to hit graph and see if you can tell me what does the number in front of x squared do to the graph. There's your original. There is 1/3 x squared. And there's 2x squared. So what does the number in front of x squared cause the graph to do? Yeah?
It changes the width of the parabola.
Yeah, it ends up having an effect on the width. And then so there's a couple ways you can think about it. Imagine like this one in red was a piece of like wood that was bent. If you glued something in the middle and you pull up on it, it would get skinnier. Right? It's like a person or like Play-Doh or something. If you pull up on it, right, it stretches and it gets skinnier. If you take something and you squish it down flat, it spreads out wider. So that's essentially what's happening here. We're either stretching it taller or we're compressing it, which causes an effect on the width. If the value in front is greater than 1, like when I graph the black one, that causes the graph to stretch vertically. The bigger the number you put in front, the bigger the stretch you get. If you did y equals 5x squared, it would stretch out even more, which would cause it to get skinnier. If you put in a decimal between 0 and 1, 1/2, 1/3, 1/10, a fraction between 0 and 1 squishes the graph, which makes it look wider, right? Squishes. So A causes a vertical stretch. When we describe it, generally we're going to say vertical stretch by a factor of, and then read the number in front. So technically, if you say vertical stretch by a factor of, say, 1/2, I know that that really means it shrunk. Because if you stretch by 0.5, it's really compressing. But it starts to get confusing if we use the word compress. So we'll always say vertical stretch by a factor of, and then put the number. So any questions on that? Now, I think somebody already tried this on their calculator, but if you put a negative and it's not inside the squaring function, this is, you do it like that. Now you're squaring the negative 1/3 and the x. Now you're only squaring the x. If the negative is out in front and it's not inside the squaring function, that also causes a reflection. But anyone know what axis it will reflect over this time? It's not the y. Yeah?
It's going to reflect over the x.
It's going to reflect over the x. Okay? So all of these graphs would open upward. If you reflected, it would cause it to open downward. Like so a negative in front of the function causes a reflection over the x-axis. A negative inside the squared function, that's a reflection over the y-axis. Any question on that? All right. So it says, how can you get the graph of negative 5x squared starting from y equals x squared? So what I'm looking for you to do is describe the transformations. I'll give you a hint. There are two. The negative does something, and the 5 does something. Let's start with the 5. Can someone explain to me in words what the 5 is going to do? Yeah. Yes. Yeah, so that's a vertical stretch by a factor of 5. And the second thing is the negative in 5. Dennis, what's that going to do?
It's going to reflect it over the x-axis.
Reflect over x-axis. Those are the two transformations you would have to do to turn this into that. Questions on how we got those two? Now, in general, there is a certain order you have to follow when you start doing transformations, like PEMDAS. I'll show you what that is in a little bit. Okay, what do you think adding or subtracting a number on the end would do? Yeah? It will what? Okay, it is going to be a shift. It could be left or right, or the other option would be, yeah? Up or down. It's one of those. So let's try putting in y equals x squared. And then let's do x squared plus 2. Let's see if it shifts up and down or left and right. Here's the original. There's the plus 2. How did it shift?
It shifted up.
Went up 2. So to get y equals x squared plus 2 from y equals x squared, you would shift the original up 2. That's how you would do it. I'm not going to graph or write the second one, but can anyone tell me how do you think you would get y equals x squared minus 3 if you had y equals x squared? What would you do to the original? Christian?
You would shift the graph down 3.
Right. To get this one, you would take your graph and shift the original y equals x squared down 3. So these are examples of what we call translations. Translations are a rigid motion transformation. What that means is it literally takes something and moves it. It doesn't cause a stretch. So adding and subtracting a number on the end is a vertical shift. And this one is pretty straightforward. If you see plus a number, it goes up. If you see minus a number, it goes down. Notice here I put absolute value because if you had something like y equals x squared minus 4, don't say it goes down -4 units. That's confusing. Down -4. Just say down 4. Down is the word negative. Right? So you can go up 4, you can go down 4, but don't go up or down a negative amount. It's like using a double negative. It's confusing. So, any questions on the idea of when you have a vertical shift? It's addition or subtraction at the end. And I guess you could write it this way too. To me, that looks kind of backwards. I would rather write it as x squared minus 4. Technically, it's the same thing. You've still subtracted 4 from the x squared. All right. Anyone have an idea how we'd make it move left or right? Yeah?
You would add it before it's squared.
Yeah, you would add it before you square it. So you use parentheses to change the order of operations. In this case, adding or subtracting first and then squaring second. Now, it is going to move left or right. minus 3, which way do you think it would move? Is minus 3 going to go left or right? Cassidy?
Right.
All right. Why do you say right? Because minus, I think negative. Negatives go to the left.
I can't explain why. I just go outside. It's to the right.
Yeah, it does. It goes to the right. It is backwards. It's backwards from what you would think. So let me write the first one down. So to get y equals x minus 3 squared from y equals x squared, which y equals x squared is called the parent function. It's the original. Move the original right 3. A lot of people say left when they see that one, but if you knew it was right, good. That's good. So we need a way to keep track of that. I mean, really, however you can remember it, that's the important thing. What I generally do is I pretend like there's a minus in every problem. So when I see something like x plus 2 squared, I think of it like this. I think of it as minus minus 2. Then, once everything is written as x minus, I block out the x minus and I look at the number that comes after it. That's a negative 2. Negative 2 means left 2. In this case, when I block the x minus, I see a positive 3. Positive 3 means right 3. So I write everything as x minus, block off the x minus, and look at the number that comes after. That's one way you can tell. So again, another rigid motion transformation. And if you write it of the form x minus, and then focus on the number that comes after the minus sign, that number tells you which way to go. If the number after the minus is positive, you go to the right. If the number after the minus is a negative, like it would be here, minus 2, I would go to the left. Again, we don't say, when we talk about shifting left and right, don't say like you shift left negative 5 units. You just say shift left 5. Now, what do we call the point of the parabola that's either the lowest point or the highest point? That's called the what? Yeah.
Vertex?
The vertex. Now, when you shift something, you're changing where the parabola is. So you could potentially be changing where this vertex is. When you shift left or right, think about the coordinate of a parabola. What part of the coordinate would that change? If you shift something left or right, it would change basically looking if it would change this part or that part. Yeah.
The x value?
It would change the x value. So shifting left and right affects the x value. Shifting up and down affects the y value. That's why when we talk about an equation written like this, which has a vertical stretch, a shift, and another shift, the h value will control where the vertex ends up horizontally. In other words, we call that the x part of a coordinate. The k value controls where the vertex ends up vertically. We call that the y value. So looking at an equation in this format, you can tell where the vertex is by looking at your horizontal shift, comma, and then your vertical shift. Okay. Cassie, did you have a question?
I think this is just me being stupid. Why, if h is greater than 0, should it shift to the left?
So when we write it like this, we're talking about an equation that's always in the form x minus, and then we're blocking off this part. and looking at the value that comes after the x minus.
Okay.
So if the value after the x minus is greater than 0, it's right, and less than 0, it's left.
Okay. Thank you.
Yep, you're welcome. It all depends on whether or not you're taking this into account when you're looking at it. Are you looking at the minus with the number or not with the number? So you can do it either way. Now, how about the line of symmetry? Think about the transformations. One of them wouldn't affect it at all. Does shifting left and right affect the line of symmetry, or up and down? One of them doesn't matter. Yeah, go ahead. Dennis? Which one doesn't matter?
The shifting up and down doesn't matter.
Up and down doesn't matter because you have line of symmetry goes up and down. So if you take a line that goes up and down and you shift it up, well, it goes up and down forever. So shifting it up doesn't matter. So the only value that affects the line of symmetry is that, shifting left and right. So if you make a move left or right, your new line of symmetry, instead of being the y-axis, is now x equals h. Yeah?
So stretching it doesn't affect line of symmetry either?
No, because if you stretch vertically, imagine you had a line that went up and down, like this, and I take that line, and it goes up and down forever, and I stretch it like that, well, it still goes up and down forever. So stretching something vertically doesn't affect the line of symmetry. Yes?
Is there a way that you would get from that equation, the a times x minus h to ax squared plus bx?
Yes. So I don't know if we're going to talk about that. Yes, we are. Yeah. So if they give you a problem, so I think this was the last page. Yeah. If they give you a problem like this, that's good, because you can see the shift left and right and the shift up and down. If they give you a problem like this, that's bad. Because what they've done now is they basically FOILed this out and subtracted 3 and wrote it as ax squared plus bx plus c. We no longer can see the transformations. So we have to reverse it. And I'll show you. You have to use factoring and completing the square. Yeah.
Okay.
But this is good. This is how we want it. We don't have to do anything with it. That's perfect. So let's start with movement left and right. How many units did I shift horizontally in this case? We'll just start with that. Yep. 2 units. And because if you think of it this way, think of it in the form x minus a number. Look at what comes after the x minus. It's a -2. That means 2 units to the left. So the vertex is 2 units to the left. And then it's also going to move how? 2 units left and
3 units down.
3 units down. There's your vertex. Line of symmetry always starts out with what letter? For a parabola. How about this? So is the line of symmetry horizontal or vertical for a parabola? Vertical. How does the equation of a vertical line always start?
Oh, y equals. Yeah, y equals.
So y equals that would be for horizontal.
Oh, okay, so
X. So line of symmetry is always going to start out as x equals, and in this case, where's my line of symmetry? X equals, think about your left and right movement. Don't worry about up and down. That doesn't matter.
-2.
-2. The line of symmetry always has to go right through the vertex. So you need the vertical line through the point -2, 3. Just like what we did in the last section. We found the vertical and the horizontal. Alright, so now there is an order that we want to follow when we do transformations in general. Like PEMDAS, it makes a difference in the final answer. In general, these are the steps that we follow when we have multiple transformations in the same problem. Step 1. Always do horizontal shifting first. Left or right. If we had a horizontal stretch, we would do that in there. We're not going to talk about horizontal stretches with parabolas, which is why I didn't write it down. Okay, so horizontal shift first. Then we deal with vertical stretching or compressing, stretch or shrink. If there was a negative in front of the stretch, then we would have a reflection. We could deal with that. And the last thing we always deal with is the vertical stretch, a shift, vertical shift. So that's the order that we want to follow. Horizontal shift, vertical stretching, reflections if we have them. We don't always have them. All of these are optional. Depends on what we have in the problem. And lastly, a vertical shift. So let's go back and let's do an example and make sure we do the transformations in the right order. Yeah.
Does vertical shift go last and horizontal goes first?
Because it's kind of like if you were solving, like, let's just say 3, how can I explain it? So if we had a parabola, 3 times x minus 2 squared plus 4, think about the last thing you would do with order of operations. First you would square, then you would stretch by 3, and then you would add 4 at the end. So does that make sense? So if you follow PEMDAS, it would be the last thing. And of course, inside the parentheses is stuff we do first. That's why this is your horizontal shift. It would be in the parentheses, and you always do parentheses first, horizontal shift. Right. Let's try this one. So, I want to know how I could get 5x squared plus 4 from f of x equals x squared. Okay. First of all, how many transformations are there in 5x squared plus 4? Okay.
There's 2.
2. Let's start with horizontal shift. Do I have a horizontal shift in that problem? Genesis? What do you think? Do we have a horizontal shift? Nope, no horizontal shift. So what's the next transformation we can go to if we don't have that?
Vertical stretch.
Vertical stretch. Do I have a vertical stretch here? Yeah, Christian?
Yes.
Yep. By how much?
By a factor of 5.
Good. So vertical stretch by factor of 5. Okay, next thing would be a reflection. Jerry, do I have a reflection in this one? No. If I had a negative 5, then I would. But there is no negative in front of it. Okay, so last thing, vertical shift. Renee, do you have a vertical shift in this one? By how much?
Going up next door.
Up 4. So shift up 4. All you need to write. We're not sketching. Any question on that? Yes?
If you're using a homework, do you want us to like tells us to do basically this? Do you want us to sketch it on our paper or just do it on the paper?
Only if it says to sketch it. If the problem doesn't say sketch, you don't have to. And if it says like find a complete graph of, then that's on the calculator. That's not by hand.
That means we're in the window, right?
Yes, find a complete graph means tell me the window. Yeah. All right. How many transformations of this one? Yep, Cassie? Yep, there are 4. Can you tell me the first one?
A horizontal shift, 1 unit to right.
Yep, so shift, right, 1. Good. What's the second transformation? Yep, Kylie.
Vertical stretch by a factor of 3.
Vertical stretch by factor of 3. Perfect. Third transformation. Oh, Jillian?
Would it be reflection in X?
Reflection which way? Say what you said again, originally.
Reflection in X.
Reflection over the x-axis. Yep, this is a reflection vertically because it's with the vertical stretch. A vertical reflection means to flip it up to down, which is over the x-axis. Flipped over x-axis. And Luke, the last one would be what?
Would be a vertical shift up. Vertical shift up 4, yeah.
Up 4. There you go. Now my vertex. Look at your shifting, and that tells you the vertex. Right 1, up 4. Right 1, up 4. And my line of symmetry. Genesis starts out with what? The destiny starts out with what letter? X equals or Y equals? X equals, good. So X equals. And what number? Again, one of these out of the shifting, one of them makes no difference at all. Jared? Yeah.
X equals 1.
Yep, X equals 1. Perfect. All right, now, as long as you're given an equation like that, that's great. But if somebody decides to FOIL this out and then distribute and add 4, that's not good. Now they've messed it up and we can't easily find the transformations. So, go back here. That format, at least our book calls that standard form, where you got the vertical stretch in front, x minus h in parentheses, squared, plus k. That's what you want. If we don't have a number in or an equation in standard form, then we need to fix it so it is in standard form. And I'm going to show you how to take something that's not in standard form and get it in standard form. So if you're given that, to change it to standard form, we're going to complete the square. So a lot of people don't remember that because it's not something that we do a lot, but I'm going to show you an example of how to do it. And hopefully it'll help you remember how to do it. The important thing with completing the square is whatever you do on one side, make sure you do on the other, like most things in algebra. So the equation we're going to look at is 3x squared plus 12x minus 18. That's the one that we're going to do. And we're done. It's going to look like this. I'm going to have a number here. I'll have an x plus or minus a number inside parentheses squared. And then I'm going to have plus or minus a number. And those three boxes would tell me exactly what my shift is, vertical and horizontal, and my stretch. So we need to change this into that. So let me show you how we do it. So the first thing when you're completing the square is you have to put the constant on the other side. So what I'm going to do is put the 18 over on the left. Okay, easy enough. So that's the first thing. And if you want to write down what we did, put the constant, or get the constant by itself. The next thing to complete the square, the coefficient of the squared term always has to be a 1. What's the coefficient I have in front of the squared term right now?
3.
It's a 3. So what I'm going to do is I'm going to pull the 3 out. Just like that. That's the second step. Now, the third step is where we find the magical number we add to both sides to complete the square. So this is the most important step. To get this number that you're going to add on both sides, so we're going to add something on both sides, you take half of the linear term and square it. That's how you get the number that goes here. Take half of the linear term, so in this case the linear term is 4x. If you take half of 4, you get how much? And what if you square it? 4. So just a coincidence here that it matches, but if this was like a 6, half of 6 is 3. 3 squared would have been 18. So take half of the coefficient of the linear term and square it. Now, you just added something on the right. You just unbalanced it. What are you going to add on the left to balance it? Yeah?
4 now. 12.
12. Good. Most people don't catch their mistake. Most people get that wrong. Most people don't correct it that quick. So, you put a 4 here, but you really added 12 to the right, so you need to add 12 to the left to keep it balanced. And the whole reason we added the number that we did is because it's going to make the right-hand side very easy to factor. Yes?
Where's the 4 coming from?
So that's half of the linear term, and you square it. In fact, maybe even better word here, half of the linear coefficient and squaring it.
So which number?
That's your linear coefficient.
Okay. Oh yeah.
This would be your quadratic coefficient. All right, so 18 plus 12 is 30. 3. And how does x squared plus 4x plus 4 factor? Yep. X plus 2 times
x plus 2 times x plus 2.
Right.
X plus 2 squared.
That's the whole point of doing what we did. By adding that special number we did to each side, it forces this to factor into something times something, and they're the same. This is x plus 2 times x plus 2. Now, we almost have it in the format we want. All we want to do is put that constant back on the other side, and how would we move the 30 back to the right? Yeah. Subtract. Now I can clearly tell you this problem is shifting left 2, vertical stretch by a factor of 3, and down 30. I couldn't tell that looking at the original problem. Like, where's the down 30 here? There is no 30. You can't see it unless you do what we just did. And that's called completing the square. Yes?
When you, from the top, when you divide it by 3 on the right, don't you do that on the left?
Nope, because I just factored it out of these two terms. The 18 was already put on the other side first. So once you put something on the other side, it's like it's in its own place. Factoring only affects one side at a time. And it is important you put the constant on the other side first. You do not want to factor a 3 out of that. And a lot of times, this step doesn't even happen. They start you off with something that's already 1x squared, so you get to skip that step. That's the hardest completing the square problem you could have. It doesn't get any more difficult than that. It can get easier. All right, so that's 1.5. So we didn't quite talk about that, so I'm going to leave that part off of the homework. Kind of has to do with quadratic formula and whether the square root comes out negative, positive, or 0. But we might have a little time to touch on that tomorrow. I don't have a ton planned for tomorrow because I know we have an assembly at 12:30. I don't think it's going to go on class, but the plan isn't to do really any new lesson tomorrow. Okay? If we have a little time, I'd like to look at that one slide, and that's the only thing we didn't do. And we can go over homework, but that's all we're going to do tomorrow. So you won't have any new homework assignment tomorrow night. This, along with page 42, is the homework for tonight. So page 42 and 56.
So you're not checking this tomorrow?
It depends. If we come back from the assembly, yeah, I'll check it. I'm going to cross off one question we didn't get to. We did not get to number 44, so you don't have to do that. Yeah, I don't think the assembly is going to go an hour and a half, so I would plan on probably being back here by like 1:15, and I'll check the homework then. I believe you're going to the assembly right from lunch.